In this project, we are analyzing performance of mass-market GNSS receivers in UAV applications. The objective is to assess the performance of various GNSS technologies in aeronautical drone maneuvers. In the two test campaigns we conducted, we are presenting the respective drone setup, the testing environments, and the results. We are finishing this presentation with some remarks on future plans. On this image, you can see how the drone was assembled. We are using a DJI Matrix drone with attached payload holders under the rotor wings. Above the rotor wings, we attach our GNSS antenna from Talisman. The antenna is then connected to a splitter, which distributes the received signals to our Spirent GNSS recorder, as well as the two onboard GNSS receivers. The processed data from the receivers are then collected by a Nuke mini computer. Furthermore, we also carry external batteries in order to power the GNSS recorder, as well as the mini computer. On the right, you can see the data flow. We are using our van in open space as an RTK base station. The collected signals on the Spirent recorder can be replayed through different receivers in order to generate a response in post-processing. Furthermore, it is also to mention that the two onboard GNSS receivers are processing the estimates based on different signals. Let's look at the different testing environments. In the first test case at the airport, we want to analyze the influence of flight speed and elevation under open sky. Therefore, we did 3 high-paced straight flight traverses at 5, 50 and 100 meter heights respectively. And since it is under open sky, we have full availability of RTK reference trajectories for comparison. In the second test case, we are flying through a forest, and here we wanted to analyze the influence of sparse obstructions due to trees. Therefore, we did 4 moderate-paced flight traverses at low height through a forest. And since it was sparsely obstructed, the reference trajectories exhibit short gaps with no traverse information. Lastly, we wanted to analyze the effect of dense obstructions by flying to a shelter. Here we did 2 moderate-paced flight traverses at low height inside an open shelter. Due to a complete obstruction, the reference trajectories exhibit large gaps with no traverse information. Here we can see the results for the airport traverse at 5 meter height. As can be seen from the table, the 95 percentile 3D error ranges from 0.9 to 1.7 meter. We want to highlight 3 observations here. First, the receiver 1 data spikes between 1222 and 1223, which coincides with an increase in drone velocity up to 60 meters per second. Therefore, we conclude that receiver 1 is sensitive towards high dynamic motions. Furthermore, we can also see that the Spirent recording are in line with the live data. Second, we replayed the gathered data to receiver 3, once with and once without S-pass correction. And in our case, the S-pass correction led to a large bias in the vertical estimation, which resulted in an increase of 0.8 meter in the 95 percentile 3D error. This hints that this receiver is not optimized for the usage with S-pass. And lastly, receiver 2 showcases a 95 percentile 3D error of around 1.7 meter. This stems mostly from its erroneous vertical estimation. If we only look at the horizontal plane, the 95 percentile of the horizontal error is only around 0.6 meter. Similar characteristics can be found for different heights, which hints that height does not play a significant role in receiver performance. If we now look at the forest and shelter traverses, an increase in 3D error can be observed as seen from the table. This is qualitatively expected due to the level of obstructions. However, quantitative analysis is not possible due to uncertain reference trajectories. Here we calculated the RTK solutions with receiver 1 and receiver 3 and took the difference between them. For the forest case, the difference is around 5 meters and for the shelter around 20 meters. Furthermore, the reference trajectories exhibit missing epochs whereby the availability of the RTK with receiver 3 is lower than the availability of the RTK with receiver 1. Similar characteristics can be observed for the other traverses in these 2 test environments as well. In order to combat this for the next test campaign, we upgraded the drone setup with a visual sensor for obstruction-independent reference data. We also did an observable analysis. Here we only consider a signal received from GPSL1 in a time window of 5 minutes. Each data point corresponds to a signal that was captured in one of the 3 scenarios. From the legend, we can see that the number of visible satellites as well as the tracking availability decreases with the level of obstructions. As an example, in the airport we have full tracking availability of 11 satellites collecting around 3000 data points, whereas in the shelter case, we only have 6 satellites at 60% tracking availability, collecting around 1400 data points. As can be seen, the forest traverse contains a wider spread of data points across the CN0 spectrum, whereas lower CN0 values are observed to have higher code noises. This is expected, since the forest canopies contributes heavily towards signal refraction. In contrast, a big part of the data points from the airport traverse are located at higher CN0 values with lower code noise values. The few outliers at lower CN0 correspond to satellites with low elevation angles. As for the shelter traverse, signal tracking was lost completely once the drone enters the covered shelter. Hence, only measurements during the part of the traverse in open sky are available. The phenomena can also be observed in this figure, where the distribution of the CN0 values is illustrated. The peaks of the CN0 values for each scenario are contributed through exposure to open sky in their respective traverse. Thereby, differences in the locations of the peaks between the airport, forest and sheltered scenarios are due to the temporal differences of the experiments and the consequent distinctions in satellite constellation geometries. For the second test campaign, we decided on the Intel RealSense camera, which records fisheye stereo camera images as well as IMU data that are stored on the mini computer. The camera should face 45 degrees downward in order to get a good trade-off of slow-moving pixels on the horizon and fast-moving pixel near the ground. We also included a new talisman antenna to collect further Galileo signals. Sensor mounts and protection parts were designed and printed. The second test campaign was conducted at ESTEC in Noordwijk and in the open fields of Rijnsburg. At ESTEC Noordwijk, we conducted experiments in 3 environments. At the football field, we analyzed the influence of flight speed under open sky, where we flew rounds with various velocities. Here we have full availability of reference information. In tennis hall, we wanted to analyze the influence of full obstruction due to closed space. Motor-paced flight rounds were conducted at different heights, and since it is indoor, we do not have reference trajectory information. Lastly, we flew around the building in order to analyze the influence of lateral obstructions due to the building walls. Here, we flew motor-paced flight traverses around the building, where we have full availability of reference information. In the following, we will show you the results of the RealSense stereo camera compared against RTK. Here we can see its performance in the building corridor traverse. The sensor is initially able to track the shape and scale of the traverse. The final area is around 10 meters after a total traverse distance of 140 meters. The large deviation that occurred on the east side might be due to the lack of distinct features in the frame. During the test at the football field, we can see that the sensor estimates a wrong scale, which might be again due to the lack of distinct features in the forward direction. We can also see that at the end of the first loop, the sensor is able to perform loop closing by recovering its pose after redetection of previously observed features. Lastly, we can see that within the tennis hall, the visual inertial sensor is still able to provide an estimate compared to RTK. During test campaign 2, further large-scale traverses with controlled velocities were performed. It is therefore interesting to investigate if the phenomena of higher PVD error at high velocity reoccurs. Furthermore, different kinds of high dynamic maneuvers were conducted, such as rapid elevation changes or yawing, in order to investigate potential correlation with PVD errors. A high number of mass market and professional receivers were tested during the second campaign. This shall give broader insights on their general behavior in UAV applications. Lastly, it is to be investigated if sensor fusion of data coming from the tracking camera and raw GNSS measurements in tightly coupled approach would increase the reference trajectory reliability.